In this lecture, we'll be looking at the problem of rupture of a thin film. Now, by thin film, we mean films where we'll be able to apply the lubrication approximation. Now, if you recall, we had said that in the lubrication approximation, the horizontal extent of the film is much larger than the vertical extent, and therefore there is a scale separation, and we can exploit this geometric ratio, this large scale separation, and to simplify the governing equations. In particular, we found that inertia drops out of the system. Now, before I proceed with the general idea of rupture of a thin film, let me explain why this would be important. Now, thin films occur in a variety of systems. In an industrial setting, we may be interested in coating surfaces, and we want to find out the coating that we've created, whether it's stable or not. Now, this could be coating of adhesives on substrates. You also encounter thin films when you have surfaces coming in contact with each other. For example, when a ball or a droplet basically hits a surface, then you have a thin film that forms. Okay. In particular, for example, if you take a substrate and you have a droplet that falls on the substrate, during impact, what ends up happening is the drop deforms. This drop deforms. And there is a thin film that forms just below the drop. Now, this thin film basically acts like a cushion, and that can sometimes even prevent the droplet from making contact with the surface. You can also have thin films in emulsions. What is an emulsion? For example, if you have droplets of one fluid suspended in another fluid, then that would be called an emulsion. Most cosmetic products are emulsions. The most common type of emulsions are what are called as oil in water emulsions. Milk is another example of an oil in water emulsion, because the milk has these flat fat globules, and for simplicity we will treat fat as just oil. You have these oil globules surrounded by an aqueous medium. And what prevents the globules from coagulating? You have this specific kind of proteins called phospholipids, which prevent these globules from coagulating or coalescing into each other. But when the milk goes bad, what we refer to as milk has gone bad, there's a phase separation that happens, and you have a thick fat layer which separates out from the rest of the milk. Now, what happens in this process? Let's take a look at it. So, for example, you have a container in which there's milk, and you have tiny droplets of oil. Now, of course, this is an exaggerated view, but you do see this image. If you were to look at milk under a microscope, you will see these tiny droplets. And if you look at, let's say hypothetically, a collision occurs between these droplets. So you have oil here, and you have oil here, and you have water. Now, in such a system, you have, when these oil droplets approach each other, they would tend to deform. And if I were to make a magnified view of this thin film region, then what you have is something like this. You have oil droplet, two oil droplets. So this oil on this side, and you have water in the middle. You have water in the middle. Now, the stability of the emulsion itself on the whole depends on interactions of this nature, and you would want ideally to prevent these interactions. And nature, for example, has devised these protein molecules which basically shield these oil droplets from coalescing to each other, right? So these introduce additional stresses called Marangoni effects and so on. Now, you also encounter rupture of thin films in other biological systems, such as, let's say, rupture of tear films. So here I'm drawing a simple sketch of the eye. This is your eye, and on this eye, what we have is a thin tear film. This tear film is formed every time we blink our eye. Now, to know whether you are suffering from a disease like a dry eye disease, clinicians would want to know how long does this take? How long does it take for this tear film to rupture? Right? So that will tell the clinician about the health of your eye, and if you are suffering from any diseases like the dry eye disease. So again, you have the same situation. You have a thin liquid film. In this case, again in the eye, it's mostly an aqueous medium, and you want to find out whether how long does it take for the thin film to rupture. You want to find out the mechanism of rupture as well. Now, rupture typically occurs in many of these systems because of a force called the van der Waals force, which we'll be introducing into this analysis. Now, to simplify the analysis and keep the problem tractable, I've considered a simple model, the simplest possible model that we can construct for the rupture of a thin film to study this problem. So we've considered a flat horizontal substrate. It's flat and it's horizontal. So gravity is acting perpendicular to the substrate. I've taken my coordinate system x and y to coincide. X coincides with the parallel to the substrate, and y is perpendicular to the substrate. And there is a thin film on top of varying height, and this thin film has a thickness given by the expression y equals h of x comma t. Now, if you notice the problem, I've clearly taken a two-dimensional setting. Though the analysis straight away carries over to a three-dimensional system. Now, we have also said that this is a free surface flow. So we are ignoring the role of the gas above. So the gas is at constant pressure and the viscosity of the gas is 0. We've already done the analysis for the interface conditions for a free surface flow, and we'll be using some of those derivations that we've done in the earlier weeks in this lecture. Now, as I already said, we'll be making use of the lubrication approximation. That's the first kind of approximation that we'll use. Later on, we'll make use of another simplification, which is the linearization of this disturbance. So now if you consider a flat undisturbed interface, let's say the thickness of that interface is h0. What we want to do is we want to perturb that interface. We want to disturb that interface. So the interface shape at an arbitrary time would be given by this equation h of x comma t. And now what we want to do is we want to find out whether the disturbance that we've given grows or decays in time. So we will assume that these disturbances are small. So that's a linear approximation that we will make use of. So we'll make use of two distinct approximations. One is the lubrication approximation, which will first allow us to simplify the equations of motion and the boundary condition. And then we will basically do a linear stability analysis on the simplified equations. So that's the strategy that we're going to follow. Now, we've already derived the non-dimensionalization procedure for lubrication approximation problems. So I've taken the characteristic length scale for non-dimensionalization of x variables as L. For y, I've taken to be h0. And for velocity, I've taken to be u0. And for vertical velocity, it's v0. For horizontal, it's u0. And we've also found out that in the discussion of lubrication approximation that we had earlier, we found that the scale for pressure that we get when we apply the lubrication approximation is the viscous scale for pressure, that is mu u0 by L divided by 1 by epsilon square. That's a scale for pressure. Now, at this point, I'm not going to define what is the scale u0, that is a velocity scale. That is because the characteristic scale u0 for velocity depends on the problem that we're taking. For example, if it's a capillary driven problem, then the velocity scale could be defined as a balance between capillarity and surface tension and viscosity. If it's a van der Waals driven problem, then it could be a balance between van der Waals forces and viscosity. So depending on the nature of the problem, I could define velocity. You could even have a gravitational spreading problem. So you could actually have a different scale for velocity. So at this point, it would be best to leave u0 as a characteristic scale for pressure, and at an appropriate time, we will define this characteristic scale for pressure, for velocity. Now, the governing equations are as follows. We have the continuity equation. We have the x and y momentum equation. Since gravity is in the y direction, we have this rho g term only, gravity term only appearing in the vertical momentum equation. Now, I'd like to remind all of you that if variables with a tilde are dimensional variables, and right now we have written down the dimensional equations. Now, we've also derived the necessary boundary conditions at the bottom, which is a flat surface. So at the bottom we have the no slip condition and the no penetration condition. And at the interface we have three conditions: the kinematic condition, the normal stress balance, and the tangential stress balance. Right? Now, on your screen you have now all the equations and the boundary conditions. Now the next step is to non-dimensionalize these equations. Let's derive the non-dimensional form of these equations. Now, terms like, I'll give you an idea. So terms like del u by del x simply become u naught by L. This is with a tilde, becomes del u by del x. Similarly, del v by del y simply becomes epsilon u naught by h naught del v by del y. But since we recognize that epsilon is nothing but h naught by L, so h naught by epsilon is just L, therefore we have u naught by L del v by del y. Therefore, that's how we write down for all the terms in the equation. So let's write down these equations. I'll write down the equations directly. So the continuity equation becomes del u by del x plus del v by del y equal to 0. Note that there is no decoration on top of any of these variables. So if they are plane variables, they are non-dimensional variables or dimensionless variables. The continuity, the equation remains as it is, doesn't change. The x momentum equation becomes del square u by del y square del x Reynolds du by dt. So again, I encourage students to try out this analysis. For example, you have a term like del square u by del x square. This simply becomes u naught by L square del square, this is with the tilde, sorry, that becomes del square u by del x square. And if you compare it to another term like del square u by del y square, you have u naught by h naught square del square u by del y square. And when we combine them and we divide throughout by u naught square by L square, then what you get is this epsilon square term. That's how we arrive at this equation. Now, we can write down similarly the y momentum equation. The y momentum equation reduces to del p by del y will be epsilon square del x square plus epsilon square. This should be y square plus epsilon square Reynolds number dv by dt. This dv by dt and du by dt of any quantity, this is the material or substantial derivative. Alright? And then we have a gravity term. So if we non-dimensionalize it correctly and make sure that the coefficient of del P by del Y is 1, that's the leading order term. Everything else is smaller than this term. It has epsilon or epsilon square and so on. Then finally here you get epsilon cube L by nu u naught times G, where nu is the kinematic viscosity and we have gravity as it is. So that's my equations. So let me label them. This is the continuity equation. This is the x momentum equation. And this is the y momentum equation. So, okay, having written down these equations, our next step is to write down the conditions at y equal to 0. As you can see, it is just u equal to 0 and v equal to 0 as it is without any change. Let's write them down. Zero. And now at y equals h of x comma t, we have to derive the interface conditions, right? So to derive the interface conditions, we have to remember a few things. For example, if you look at the normal stress balance and the tangential stress balance, you have the derivative of the height. So we have hx tilde. This is nothing but del h tilde by del x tilde. And if you non-dimensionalize it, we have for h tilde we have h naught, and for x tilde we have L, that is del h by del x. But we also know that h naught by L is epsilon, therefore that is epsilon del h by del x. So you see that the height derivative del h tilde by del x tilde essentially becomes epsilon del h by del x, right? So we'll make use of this simplification. Let's start with the kinematic condition. Kinematic condition, all these conditions are, remember, are at y equal to h of x comma t. The kinematic condition essentially we have v equals del h by del t. V tilde is del h tilde by del tilde plus u tilde del h tilde by del x tilde. This should be h tilde, sorry. So now this equation, if you work it out, you will exactly get the same. You will get v tilde will be del h tilde by del t tilde plus u tilde del h tilde by del x tilde. This simply becomes v is equal to del h by del t plus u del h by del x. No change in this equation. Now the normal stress balance, I'll do it a little slowly to highlight what are the key terms that enter in the normal stress balance equation. So let's start by writing down what is the normal stress balance in the dimensionless form straight away. So we have minus P times PC plus 2 mu. So we have terms like, okay, let's write down P infinity minus P. So that's, we have P infinity minus P, this times PC. That's what we have. And then we have these viscous terms here. The viscous terms, essentially you have, if you see here, you have a lot of hx derivatives, right, in this term. So let's write that down. Plus 2 mu. So first is we have hx square minus 1. That becomes epsilon square hx square minus 1. 1 plus epsilon square hx square times ux. Ux becomes u naught by L times hx, and then we have minus hx by 1 plus hx square, that is epsilon hx by 1 plus epsilon square hx square times uy plus vx. Uy plus vx essentially becomes u naught by h naught into uy. V tilde x tilde essentially becomes epsilon u naught by L into Vx. That's my u tilde y tilde plus V tilde x tilde. That is uy plus Vx. That's my norm. And on the right hand side we have gamma hxx. That is h naught by L square, right? H naught by L square times hxx by 1 plus epsilon square hx square whole power 3 by 2. That's all the terms that we have got here. So now we will use, we know that the scale for pressure would be mu u naught by L into 1 by epsilon square. Let's make use of this. What do we have here? We now have P infinity minus P times Pc, that is mu u naught by L times 1 by epsilon square plus 2 mu. So we have epsilon square hx square minus 1 by 1 plus epsilon square hx square times u naught by L into hx. That's the first step that we have, first term that we got. Then we have minus epsilon hx by 1 plus epsilon square hx square times we have u naught by h naught. Remember, u naught by h naught essentially becomes u naught by L into L by h naught, right? So this term essentially becomes u naught by L into 1 by epsilon. Okay, so let's write that down. We have 1 by epsilon uy plus epsilon u naught by L Vx. Okay, so the simple rough work that we have done here, we'll put it in a box here. So that completes the viscous term here. And on the right hand side we have gamma h naught by L square. Gamma h naught by L square can also be written as epsilon gamma by L, because h naught by L is epsilon, times hxx by 1 plus epsilon square hx square whole power 3 by 2. Okay. Now what we can do is we can multiply throughout by L by mu u naught into epsilon square. Okay. So what does it immediately do to us? So if you see the equation, the coefficient, this term I have taken and I'm dividing throughout by this term, so that the coefficient of pressure becomes unity. So I immediately have P infinity minus P, right? And then I have 2 mu epsilon square L by mu u naught. That's what I have, right? And we have epsilon square hx square minus 1 by 1 plus epsilon square hx square u naught by L hx. That's what I have. I have here I've missed something here. I've missed a u naught by L. Sorry about this. So in the uy term, just correct this thing here. There should be u naught by L. Just correct this u naught by L there in that term. So I have epsilon hx by 1 plus epsilon square hx square times, if I take u naught by L, u naught by epsilon into L, if I take that common, I'm going to get uy plus epsilon square Vx, and then on the right hand side I have epsilon gamma by L multiplied by epsilon square L by mu u naught times the curvature term, 1 plus epsilon square hx square whole power 3 by 2. So now I have all the terms in the equation, and so now let's do some simplification here. So straight away mu cancels out here, and on the right hand side you have L cancelling out. Now we also have L by u naught, right? This L by u naught, this term here that we see here, cancels out u naught by L and u naught by L terms, right? So and then further I also have one more cancellation that I can do. I can cancel out this epsilon over here with the epsilon in the denominator, in the second term, in the viscous term. So now let's simplify this equation. What do I have here? I have P infinity minus P plus 2 epsilon square times epsilon square hx square minus 1 by 1 plus epsilon square hx square into hx. Sorry, this should be ux. Sorry, make the correction. This should be velocity ux in the previous terms as well. This should be ux, okay, minus hx by 1 plus epsilon square hx square times, what do we have here? We have uy plus epsilon square Vx. This is equal to, on the right hand side what we have is epsilon cube gamma by mu u naught times hxx by 1 plus epsilon square hx square whole power 3 by 2, right? This is what I have. So notice that this term, this entire term here, the viscous term, is viscous term are order epsilon square or smaller. There's an epsilon square sitting outside, okay, and every other term that we have here is either epsilon square or it's even smaller. We even have, for example, the last viscous term that you see that has an epsilon square Vx. So that's a order epsilon to the power of 4. So we know that these are small terms, small compared to what? Compared to the order 1 terms on the left hand side. Okay. What about this term? Now if you notice here, this is epsilon cube divided by mu u naught by gamma. This is nothing but epsilon cube by capillary number. Is this term small? We cannot comment at this point. The reason for that is because we do not know the value of capillary number. So a new non-dimensional number has naturally entered the problem, and that's expected because this term is, I've chosen a scale for pressure to be the viscous scale, and on the right hand side I have curvature term, which is a surface tension term. So whenever I have a ratio of the viscous scale to the surface tension scale, we should expect a capillary number. So that's exactly where it shows up. Now if capillary number is comparable to epsilon cube, then that's an order 1 term. But if capillary number is much smaller than epsilon cube, then the term becomes very important, right? Whereas if capillary number is order 1, then you can safely say that surface tension is not important. So this actually tells us, it also tells us what is the typical range of capillary numbers that we should expect for a lubrication, in the lubrication problems where curvature is important or not, right? So instead of writing out the whole equation, what I will do is, for simplification, I know that these terms don't matter for what's going to come. So I'll just say P infinity minus P plus order epsilon square terms. Okay, order epsilon square is the leading order terms. Okay, this is equal to epsilon cube by capillary hx6 by 1 plus epsilon square hx square whole power 3 by 2. That's what we get. This is my normal stress balance. Now let's write down the tangential stress balance. Remember that the tangential stress balance is given by this equation u tilde y tilde plus v tilde x tilde multiplied by 1 minus hx square minus 4 ux hx with the tildes is equal to 0. That's what we have. Now let's write down the non-dimensional version of this equation. So I'll straight away write down the non-dimensional version. What do we have is u tilde y tilde. So that becomes u naught by h naught uy plus v tilde x tilde, that is epsilon u naught by L Vx. This is what we have, the first term, minus 1 minus epsilon square hx square minus 4 u tilde x tilde, that is u naught by L and h tilde x tilde, that is epsilon into ux hx is 0. Right? Now if we note that epsilon is h naught by L, I can simply replace this first term by 1 by epsilon into uy plus vx. I have a u naught by L on the outside, 1 minus epsilon square hx square, and then I have 4 epsilon u naught by L ux hx is 0. I can safely cancel this term on both sides in both the terms, and so now I have uy plus epsilon vx times 1 minus epsilon square hx square minus 4 epsilon square ux hx is 0. That's my leading order. That's my tangential stress balance. So now is a good time to summarize all the equations. But before we do that, we can make one more simplification. Now if you notice all these equations, so for example, these are the non-dimensional momentum equations. The non-dimensional momentum equations, if you notice, I have grouped them into two parts. On the left hand side, we have the leading order or the order 1 terms, that is terms which do not have an epsilon. On the right hand side, we have terms of size epsilon or epsilon square or epsilon square Re and so on. Now I've done the same thing in the kinematic condition remains unchanged. As far as the normal stress balance is concerned, we again have the same thing. We have separated them into order 1 terms and order epsilon square and smaller terms. The exception is this term, epsilon cube by Re. At this point, we will not comment on what is the exact size of it. We'll retain that term because we do not know the value of capillary number in a given problem. In the tangential stress balance, again we have the same thing here. If we were to simplify this further, we have uy is equal to, or let's retain this as it is, and we will simplify this equation. Now how do we simplify these equations further? Now the easiest way to simplify this equation is using a perturbation expansion. Okay. Now in perturbation theory, the first thing to look out for is a small parameter. Now we have not one but two small parameters. Okay. So let me write this down. So we have two small parameters in the problem. One is epsilon and the other is epsilon square Reynolds number. We will set both of these small parameters. We'll set both of them to be much less than 1. Okay. So in other words, what we have is we have epsilon much less than 1 and epsilon square Reynolds number will also set it to be much less than 1. The second term, that is epsilon square Re, it's very convenient to think of this term as being, how do we achieve this condition of epsilon square Re being small? You can say I'm setting Reynolds number to be finite and fixed, and the epsilon square times Reynolds number is much smaller than 1. In other words, the size of this term I can vary it by varying the value of epsilon. Okay. And what does this allow me to do? It allows me to expand all the terms in terms of epsilon. So we will carry out an expansion in terms of epsilon. Okay. What does that essentially mean? It means that I will expand all the variables in some powers of epsilon typically, but since we do not know the exact powers of epsilon, we will just do it in terms of arbitrary gauge functions. So let's do this. So for example, I could say u is in this case x, y and t is some u naught, that's a leading order, plus f1 of epsilon u1 plus so on. So f1 is some arbitrary gauge function of epsilon, and we know it's much smaller than 1. That's the condition. So similarly, v is v naught plus f2 of epsilon, pressure, and finally we have an expansion for the height. H comma t is some h naught, which is also a function of x comma t, plus some unknown f4 It is possible to determine exactly what these gauge functions are, but it suffices to say that f1, f2, f3 and f4, they're all much smaller than 1. It's sufficient for us because the focus in our analysis is only on the leading order terms. So if we substitute these expansions into the governing equations, what we get is we get the leading order equations. What are the leading order equations? Substitute the above expansions into the above non-dimensional equations. Okay. Let's start with the continuity equation. The continuity equation becomes simply becomes del u0 by del x plus del v0 by del y is equal to 0. Only the leading order. Remember, leading order means these are order 1 or order epsilon power 0 terms only. That's the meaning of leading order. Alright. So we have the continuity equation. Let's write down the x momentum equation. The x momentum equation becomes del square u0 by del y square minus del p0 by del x 0. The superscript 0 indicates that we're only writing down the equations for the leading order. Then we have the y momentum equation. That becomes del P0 by del y becomes epsilon cube L square by nu u naught times g. That's what we have. I just realized that I have not put an L square there. I think there should be, please correct this term, there should be an epsilon cube L square. Okay, that should be an L square on the right hand side. So we have written down all the equations. Now, just like the argument that I gave for the normal stress balance, where we had the Capri number, we have the same requirement even here. I have not removed this gravity term because at this point I do not know the exact value of this non-dimensional quantity. Epsilon cube is compared now to this new quantity, which is L square into g by nu u naught. Till I know the value of that quantity, I cannot actually straight away say that it is very small. But even if it was very, very small, you will see that it does not matter to the analysis, because what matters for the x momentum equation is the pressure gradient in the horizontal direction. Okay, so this will not eventually matter in any case, but let's retain it for the sake of accuracy. Now let's write down the boundary conditions. At y equal to 0, we have u leading order, and leading order v is also 0. At y equals h of x comma t, what we have is we have v is del h by del t plus u del h by del x. Okay, I just made one small error here. We don't need to do an expansion in h, so we can get rid of this. It's sufficient to only make an expansion in u, v and p, right? So we've already made use of the lubrication approximation, where h essentially becomes is much smaller than the horizontal length scale. So the boundary conditions are applied at y equals h at this point. So we have the kinematic condition, we have the normal stress balance essentially becomes P infinity minus P is equal to minus epsilon cube gamma, or minus epsilon cube by capillary number times hxx. I don't need to, again, as I said, we don't need to do an expansion in h, because these terms, if you look at the tangential stress, no, normal stress balance, the denominator has 1 plus epsilon square hx square. This 1 plus epsilon square hx square essentially becomes very, very small. Just to illustrate here, you have 1 by 1 plus epsilon square hx square whole power 3 by 2 essentially becomes 1 plus epsilon square hx square whole power minus 3 by 2, and this becomes 1 minus 3 by 2 epsilon square hx square by binomial expansion, and this is an order epsilon square term and is small. So that's how we get rid of all the other complex terms. So we have this term, pressure, the normal stress balance, and I should mention that this is a leading order pressure term, and finally the tangential stress balance simply reduces to del u0 by del y is 0. So we have the kinematic condition, we have the normal stress balance, and we have the tangential stress balance. So now that if we have all these equations of motion along with boundary conditions, we have a closed set of equations. We still haven't introduced forces like the van der Waals force, but we will take it up in the next lecture. So what we want to now do is to take these equations and then perturb the interface and see what's the linear stability of the system looks like. So that's what we will be doing in the next lecture. Thank you.